Let's move on to residue Z. So again, this is a theoretic approach. We're going to end up with an analytic solution, a formula, not a list of numbers, but we're going to use MATLAB. And the easiest way to do this is just to give an example. So you've got this big long x of z here, this ratio of polynomials. You know this would be painful to do a partial fraction decomposition by hand. This particular one, is this, Jeremiah, is this a proper fraction or an improper fraction?
That is not proper.
That is not proper, correct. We always want the denominator to be bigger than the numerator. And here, the m in the numerator is 4 and the n in the denominator is 3. So it's definitely not proper. So,
sir, quick question. Are we throwing away the negative sign in this case? Is that why the 3 is considered bigger?
You're not throwing it away, but it comes because if you were to put this in terms of positive powers of z, we'd have to multiply the numerator by z to the 4 and the denominator by z to the 3. And then the greatest power of z in the numerator would be 5 times z to the positive 4 and 1 times z to the positive 3. And so we want to get the power of z greater in the denominator. So you can think of it as throwing away the negative, but I wouldn't. I would, yeah, think of it as ignoring the negative if you want to, as long as you've got it in correct notation, which means these are both scalars. If this was a 5z to the negative 1 minus this thing times z to the negative 2, blah, 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 times this thing to the z to the negative 4, you'd have to divide through by z to the negative 1 so that this is a scalar, not a power of z, and this is a scalar, not a power of z. Does that answer your question, Fawaz?
Yes, sir.
Okay. So now just throw it into, so now you don't need to worry. If you're using residue z, you don't need to worry about making it proper. MATLAB does it all for you. You do need to get it into correct notation, though, before you throw it into MATLAB. And by correct notation, I mean these things have to be scalars. And if they're not, there's going to be a z to the negative 2, say, out here, or z to the negative 3, and you'll just have to remember that. MATLAB can't take that into account. If you throw this into MATLAB, it's numerator in decreasing powers of z, it's then denominator in decreasing powers of z, residue z, and it gives you an r, a p, and a k value. Here's your r, p, and k that corresponds to this particular one. And the r, think of roots. I'm sorry, do not think of roots. R, think of the numerators. This is what you'd get with the cover-up methods. The r corresponds to your a's and your b's and your c's from the partial fraction decomposition. Your p's are your poles. And so here you can see this has got a repeated root at 1, and it's got a unique root at -2. And then your k is the part that you divide through to make this thing proper if you're doing it by hand. So your k's firstly go in decreasing powers of z to the negative 1. So it's plain old -3, plain old z to the negative 1. You know what this transforms into. This is -3 times an impulse, and this is an impulse delayed by 1. And then here, your r factors go in the numerator, and your poles go in the denominator. And in the special case that you've got repeated poles, like here, it's the pole that's not raised to a power first, and then the second one, it's the pole that's raised to a power. And if you had more powers than that, there'd be another pole at 1, and then the next thing would be 1 minus the negative 1 cubed, and so on. And then from here, you can directly take the transform using your tables. And the only catch would be to get this in a standard form, meaning these things both not powers of z, decreasing powers of z. What if you ended up with a z to the negative 2 outside of the whole thing? Then once you took your inverse z transform, then you'd replace every n with an n to the negative 2, corresponding to that z to the negative 2 on the outside. Questions on that? That's a lot of stuff.